This is the ROS Developers Podcast, episode 119.
The ROS Developers Podcast, the ROS Developers. The ROS Developers Podcast, the ROS Developers.
Hello, ROS developers, and welcome to the ROS Developers Podcast, the podcast that gives you insights from the experts about how to program your robots with ROS. This is Ricardo from The Construct, watching myself on the mirror camera. So, and today I would like to dedicate this episode to all those people that are struggling setting complex networks of ROS2 devices with several robots that are across different lands. So if you are struggling with this, then this episode is dedicated to you. And today we are going to talk about communications between different robots and also systems over a large network and even over internet. But before going into that, let me tell you about The Construct. Is a company where you can learn everything about ROS1 and ROS2. So we have developed our own courses which are practice-based. So that means that it's not just watching a video. Actually, we don't have videos in our method. You start practicing from minute number one. So you have the different lessons that you have to follow. You have a simulation of the robot, and then you have to target that robot. Create from minute number one. You are going to be doing things with that robot, and you can see if your program is progressing or not, because the robot will do what it's meant to be. Also, as you progress with the different courses, you will be able to connect to our real robots. So we have some real robot labs here in Barcelona, and you will be connecting from your location to our robots and practice on those robots. So the whole system is automatic. You don't need any special setup. Open the course and then connect to the real robot, and then you will see the camera of the real robot here in Barcelona. You can control it and do your tests there. Check it out because it's a very fast way of learning about ROS. ROS1 and ROS2. We have both. And many other subjects related to robotics. So, I will put a link to this on the show notes here beneath. And I think that now we go to the meat of the episode, right? You're waiting for this. And so let me introduce you, Julien Enoch. Julien is a senior solutions architect at ZettaScale Technology, as well as he is also Eclipse Zenoh committer. Today, Julien is going to talk about what is Zenoh and why we should use it in our ROS2 robots. Welcome to the podcast, Julien.
Hi, everyone. Hi, Ricardo. Thanks. Thank you for your invitation. It's a pleasure to be here with you today.
My pleasure today, and Julien, he's been preparing very, very well for this podcast interview, and you will see by the end that we have a small surprise. So this podcast also includes practice with Zenoh.
Exactly, live practice. Yeah.
Okay, very good. This is building momentum, so the people want to stay on the podcast and keep listening to that. Okay. So. I was very interested to interview you. So we have been several months after this interview, right? Since the ROSCon 2022, because I started to hear there, and you were there in Kyoto, Japan, and then you presented there about Zenoh. And so I was very interested to know more about this subject. So can you explain to the audience what is Zenoh and where does it comes from?
Yes. So Eclipse Zenoh is an open source middleware for communication. So really the target is really to ease the communication between any kind of machines, any kind of microcontroller units or whatever hardware that needs to communicate with each other and with the cloud, of course. So already you can classify Zenoh in the similar groups than MQTT, DDS, AMQP, gRPC, all those kind of middleware with programming API for communications between various softwares.
Okay. Okay. And yeah, and why did you decide to take to develop this Zenoh? There are, you mentioned many already communication systems frameworks.
Yes, because actually the history of group, right? We the core of the Zenoh team and ZettaScale company in global is really a set of people, a core people that are working for a very long time, more than 20 years, is in communication middleware, right? For me, for instance, I was working at the beginning of the 20th. Of 2000, sorry,
2020?
2000, right?
2000.
I started my career here working with Corba.
Corba.
Middleware, which was really, yes, long time ago. That's middleware from the 80s, from the 90s, which were used in industry, in telecommunication, in transportation, and so a lot of various use cases. And then I also worked since the very beginning with DDS, data distribution service, that is actually in the core now of ROS2.
Mm-hmm.
And yes, and also we also experimented, of course, with other a lot of various middleware for communication to compare really the benefits and the others. So with all this experience, actually, we sense that there was some lack in all those middlewares, right? Because sometimes you want to have publication and subscription, like in DDS, but also sometimes you would like to have some comments and request reply. And actually, ROS2 is combining both, right? ROS is combining the both. There are the topic where you publish, you subscribe, but you have also the services. You have the actions for which you send a request and you expect a reply.
Mm-hmm.
And actually, well, there are very few, if barely known, middleware that combine the both. So that was our first decision, really, to start to push something, new middleware that actually combines those two paradigms, pub/sub and request reply, but also actually to add the storage of data, because in a lot of middlewares, right, you would like to publish, but also to store your data and later on to get back your data with a request.
Wait, what does it mean to store the data? Because the data in a subscriber system, so you publish and then the subscriber gets the data and then you can do whatever it wants. So it can store in the local memory or in a hard disk or...
Absolutely, it can do it. You can implement it by yourself, right? But wouldn't it be nice if all of a sudden in your system you declare, okay, I want to deploy a storage that will store all the publication for this topic in a database, in InfluxDB, in a ROS bag,
yes,
in a file system,
yes,
wherever you want, right?
Okay.
And later on, with the same middleware, you perform a get operation that will retrieve your data, right?
Yes, and you can then you can reply what has been said before, right?
That's a use case, for instance, replying. Yes, that's a very very common use case. But also for analysis, for instance, right? Sometimes you would like to perform some analysis on the latest publication or a set of publication, just to compute an average or something, right? And also for logging, for security logging, right? In the automotive industry, for instance, it's very important to log all what can happen as in the middleware as publication, subscription, to later on, in case of accident, for instance, to have a log, an evidence of what happened. So that was a set of use cases. So we were involved actually in the past, in the last 10 years, with some use cases involving also some large scale and also communication to the internet. So with DDS, for instance, we were involved in some POC for smart cities, for the Nice city, for Barcelona city, actually, with Cisco. We perform a POC for fog computing in Barcelona with Cisco. And well, DDS, of course, was used for this because that's what we were working on at this stage. And actually, we experimented some issues as soon as you get out for a LAN with DDS. So that's why it was more than 12 years ago now, we built a product which was named Vortex Link, which was actually the very first discovery on routing service for DDS.
Okay.
So because DDS mainly works very well as soon as you are in a LAN, in a very close environment with low latency, with high bandwidth, with not so much loss of messages, right? Everything is perfect, and the QSs are very wonderful for this in DDS. You can tune everything in terms of message exchanges. But we saw that as soon as you get out of these closed environments, where you go over the internet, you increase the latency. Where you go over wireless network, you have loss of messages, right? And in this case, DDS suffered some issues. Robotics using ROS2 are very aware of.
Yes. Yes.
Yeah. So at this stage, 12 years ago, we tried to build this Vortex Link product, which was actually an extension of DDS for the cloud, for the edge and cloud computing. And what we did really, we wanted to focus on the DDSI protocol, so the protocol which is standard, which is at the core of DDS, and we tried to adapt what we did to this specification to be compatible with all the DDS vendors, and then to route from end to end, so from the devices in your local area network up to the cloud, all the DDS traffic. We had some success with this, but finally we saw that the limitation of this approach because really of the DDSI specification, which we should really contortionate, if I can say, to adapt to what we wanted to do and what is required for communication over the LAN. So with all this experience from the past, we decided, and actually that's the vision that our CEO and CTO, Angelo Corsero, had more than 10 years ago, so 15 years ago, about the fog computing and what is required for fog computing, really to have a continuum of data connectivity from the devices, wherever they are, to the edge, to the gateways, to your LAN, and then up to the cloud.
Okay, wow, that's a long story. So it has a past, even if for us, I think that for the ROS community, it's something like is very new. So it sounds, actually I didn't know that I have heard something before the ROSCon, but something like, well, so many things in ROS. Then from that conference, I think the people got interested from that. But it looks like you just presented this year, Yes.
No, actually, yes. The company is quite new, yes. ZettaScale is relatively new. It has just 1 year, little more than 1 year of existence.
Oh, the company. That's a company. Yeah. Okay. ZettaScale, right?
Yeah, ZettaScale is a company which is managing Eclipse Zenoh and also Eclipse Cyclone DDS.
Okay. Okay. Wait. You mentioned here too much information. So what are those two versions? Eclipse Zenoh and Eclipse DDS, right?
Eclipse Cyclone DDS. So
Cyclone, yes, Cyclone.
Yes, that's one of the 3 or 4 DDS implementation available on for ROS2.
Yes.
So ZettaScale, we have the team supporting Cyclone DDS is hired by ZettaScale. Right?
Okay. But what's Cyclone was developed in AD-Link, isn't it?
So actually, ZettaScale is a spin-off of AD-Link.
Okay.
All the group, yes, that's all the same group. So to come back to the history of this group of people that are making ZettaScale right now.
Yes.
In the past, we were coming from PrismTech company. So PrismTech was a company doing support for Corba technologies in the past, but also for DDS technologies. So PrismTech was also at the very first company specifying the DDS with RTI at the OMG. So that was more than 10 years ago now, almost 20 years ago. And so we had a product named Vortex Open Splice. That was our very first implementation of DDS that actually came from Thales Group, but which was supported by PrismTech.
It was used at some... sorry to interrupt. It was used in some of the early versions of ROS2, so you could use it. I think that now is not possible, if I'm not wrong. Splice.
Sorry, I'm not aware of
Okay.
this.
Don't worry. Sorry to interrupt you. Sorry. Go ahead.
Yes, so Open Splice was the very first version of DDS that PrismTech supported. And later on, a few years ago, we decided to go on with a fresh implementation, more lightweight, which is Cyclone DDS. And at the same time, PrismTech was acquired by ADLink technology.
Oh, okay.
So that's why Cyclone DDS, yes, at some point was a product from ADLink.
Mm-hmm.
And at the same time, we also started the Zenoh project, which was also a product for ADLink.
Uh-huh.
And then ADLink was decided and saw the potential of Cyclone DDS and the potential of Zenoh. And with the agreement of Angelo Corsaro, our CEO, they decided to create a new company, independent company from ADLink, which is ZettaScale. Okay. And this company is really dedicated to those two middlewares, Cyclone DDS and Zenoh.
Okay. Now I got the picture. Okay. Clear. Yeah. Great.
Yeah, that's long stories. That's things that happen in the life of companies, right? Acquisitions,
it's like
rebranding and so on.
Yeah, it sounds to me like Game of Thrones, so many different. But because also I want to introduce something that you keep mentioning, so I think it's important. So what is all this related with the Eclipse Foundation?
So from the very beginning of Cyclone DDS and then also of Zenoh, we decided to go open source. So to have this open source to create a community and also to benefit from the feedback of users, but also from contributions of users. That's really important to create an ecosystem. And so Eclipse Foundation is a foundation which manages a lot of open source software. It started with the Eclipse IDEs that a lot of people know, but they also are also managing a lot of software for IoT and edge computing. Right? They have this working group for IoT and another working group for edge computing. And so, yes, it was a perfect fit for us, right, to go into this foundation that give us really a well scope for our software and also good practices, right? They have a license, their own license, which is an open source license. They provide some guarantees of check of the dependencies, so to be sure that in the software that are released by the Eclipse Foundation, there are no dependency to licenses that might be not so open source or may have some restrictions. And also they provide some guidance on the way to drive, to manage an open source project and to manage a community around an open source project. So yes, ADLink and ZettaScale decided to give these two projects, Cyclone DDS and Zenoh, to the Eclipse Foundation, and to be a contributing member to the Eclipse Foundation. So we keep to commit for the two projects. We are the main committers for the two projects, but any people wanting to be in the project can be involved, whatever company is, right, and can join the Eclipse Foundation and become a contributing member and also an individual committer to any open source project hosted by the Eclipse Foundation.
Okay. Yeah. Well, all this about foundations is another subject. So now I understand the relation between all of that. But we are not going to go into the foundations and how they work and how, because too complex. So let's go to more technical details. Then the question is, so you have mentioned about this implementation of Zenoh, and then so if we have already our DDS in ROS2, so why would we need, as a ROS developer, why would we need to use Zenoh?
Okay, so, well, as I mentioned in the first point, you might need Zenoh, for instance, to go over wireless networks, right? You need to know that in DDS, for instance, because there is this all those QSs, you need to have a matching between a publisher and a subscriber. So you need to have the full discovery of each publishers on each subscriber, and each publisher needs to accept the subscribers to see if the QS are matching or not, and each subscriber needs to accept the publisher to see if the QS are matching or not. Mm-hmm. So it means that in a robot, for instance, if you have 10 or 50 or 100 of publishers and subscribers, at the startup time, they all are exchanging discovery information with each other to discover each other and to check if the QS are setting and so on. Yeah. Uh-huh. So even if it looks like peer-to-peer communication, it's really publisher to subscriber communication, and you need a full discovery protocol to do this. Unfortunately, if you are on wireless network, this protocol runs most of the time on UDP multicast and then UDP unicast also. But with UDP, you may have message loss, right? The DDS implementation are reliable. It means that they are able to retransmit the message which are lost. But if they retransmit it, it's some exchange of message, and it's some more traffic to handle by the network, right? And what may happen if you have a disconnectivity, for instance, of your wireless network, is that at reestablishment, you get all this flooding of discovery messages that comes, and then can also make your wireless networks to collapse again.
Yes, exactly.
You might, in some cases, you might end in an infinite loop of discovery, disconnection, and so on.
Yes, and the effect in ROS2 is very strange. So sometimes you cannot find some topics, but then later you can listen to them. But so you get the messages, but then it's a strange effect, and you don't know where is the problem.
Yeah, well, it's mainly because of the quality of the network behind, mm-hmm. right? If you test everything in a wireless, in a Ethernet LAN, you won't see this problem. But as soon as you go on wireless networks with lots of messages, with more latency, with constrained bandwidth, you get into possible troubles. Mm-hmm. So the first point on which you might want to use Zenoh is really for this point. What we developed with Zenoh is also a bridge to DDS. Okay. And this means that we can deploy on any robot just a piece of software, just an executable that will act as a DDS participant, so that it will discover all the readers, writers, but internal to the robot. Mm-hmm. And then on the external, for external communication with other hosts, it will transmit all the publication and subscription to Zenoh.
Okay.
And Zenoh, the discovery protocol of Zenoh is far more efficient than DDS, because in Zenoh, actually, first we halve the discovery with only propagating the information for subscription, not publication. We don't have all the QS settings that might exist in DDS, so we don't need to perform this close matching between each readers and writers. And also we have some other techniques really to compress all the discovery information.
Okay. And then one question, then if we have several robots in that LAN, in that wireless network, then we need to have this bridge in each one of the robots, or is one per for the whole fleet of robots?
So actually, it's as you wish. But you're right. If all your robots are connected to a wireless networks, we strongly advise to have one DDS bridge to Zenoh per robot.
Makes sense. Yeah.
And then to keep the DDS communication local to the robot with the environment variable ROS localhost only equal 1.
Okay.
So everything in DDS can kept localhost with the loopback, or in some cases, for instance, in shared memories, thanks to ISORIX, for instance, that is a deployment option for Cyclone DDS. And then all the communication to the network will go over Zenoh. And moreover, in this Zenoh bridge, you can configure it to decide which topic you're allowed to go over the network. So you're not forced to have all the topics. Lot of topics are only internal, are only interested for the various ROS components inside the robot, but you don't need to publish them outside.
Exactly. For example, I have a point cloud device in my robot that is needed for it in order to navigate or discover things, identify objects. But then, so I want to have my robot available in the whole network, so everybody in this network, which is Wi-Fi, can control the robot or send to them navigation commands to go to one place and so on. For that, I don't need this point cloud topic. So what's the purpose of discovering this topic, right? And sharing with all the other elements of the network. That's the point, right?
Yes, exactly.
Okay.
And another point is the frequency of publication, right? For instance, in a robot, most of the robots, you have the battery state, which is published at 10 or 20 hertz.
Wow.
But it doesn't make sense. I just need to know the battery state every 5 seconds or every 10 seconds. Right?
Yes.
So in the Zenoh DDS bridge, you can configure for each topic the frequency of republication over Zenoh. So I can decide my battery state. I will republish at only 0.1 hertz, for instance.
Yes, in this case.
Again,
sorry, go ahead.
Again, that's a save of bandwidth.
Yes.
You're more efficient. You will not flood your networks for nothing.
Yeah, it's like you, and then in this case, by using Zenoh, you are kind of taking decisions based on what is required in order to transmit the data. So instead of DDS, that DDS is like blind transmission. So it says, hey, I'm going to provide you this service, which is the DDS communication, but I don't care what you do or whatever. So this is the channel, send it. And that's it. But on Zenoh, it's like, no, you are taking into account the actual things that matter for that application.
For the bridge, yes. That's really a specificity of the DDS bridge to Zenoh. Right?
To Zenoh, exactly.
In DDS, there are also some other solution to perform this with the QoS settings in DDS. But that's very complex to set up, right? And you need to configure this for each readers and writers.
Yes.
And often you need to configure this programmatically.
Yes, and you don't know, sometimes you get confused, you don't know the other side, and then you don't know what is happening because the topics are there, but they are not communicating, and it's because of this, so it introduces a lot more of problems.
Yes. Exactly.
Oh, okay.
And then another benefit of Zenoh is that we provide what we name a software router, the Zenoh router. So DDS is peer-to-peer communication, right? MQTT, for instance, is brokered communication. You have one MQTT broker, you have the publisher and subscriber connecting to this MQTT broker that do the mediation between all of this. With Zenoh, we introduced a router, which is actually a little more than a broker because you may have a network of those routers interconnected together in whatever graph you want, click or mesh communication, mesh deployment, right? And you can have also Zenoh clients or Zenoh peers connecting to those routers, and the routers will always find the correct path from one client application that is publishing over Zenoh to another one, wherever it is, which is subscribing over Zenoh. Right.
Okay, and that is called a router.
Sorry, go ahead.
Yeah, sorry. And this is called the router. So the one that is the Zenoh router.
Yes, it's called the Zenoh router. Yes, it's a software which we provide in the open source version. You can build it from the sources which are on GitHub, or you can download it. We perform the releases. You can download the release of this router. So, and what it allows for robotics, for instance, let's say you have your robot behind a NAT, right? And you have two systems which are each behind two NATs, and symmetric NATs.
Mm-hmm.
You can't have those two systems communicating with each other, right? They can't address those because the NAT prevents this.
Mm-hmm.
Right? So what you can do with Zenoh is that you can deploy a Zenoh router somewhere in a public host, so in the cloud, public IP. You have your two robots with the Zenoh DDS bridge. You configure those to connect to the router. And all of a sudden, you have a full connectivity between your two robots, which is going from the first bridge to the router, then to the second bridge, then to the second robot.
Oh, that's awesome.
And you can multiply the number of routers, so to combine several places where your robots are and drive them, monitor them from anywhere in the world.
Okay, that's a very interesting solution. Also, for in our case, it happens that some universities or some students that are behind a firewall that is configured, I don't know how, they don't even know, and then they connect to our academy courses, but sometimes they cannot see the cameras that we are publishing, or they cannot see, for example, the RBIS, the RBIS, they cannot see the topics, and this is because this firewall is blocking. We have done some tricks and managed to do, but still, in some cases, we keep reporting those things. Then in that case, we can implement, for example, this solution. So our clients, the students, they connect to this Zenoh router, and we publish from our lab, we publish into that Zenoh router. So then the communication is established automatically, right?
Absolutely, yeah.
Okay.
Because actually, the only thing you need is really an outgoing TCP connection.
Mm-hmm.
Once from your NAT, you can always, except if you have a proxy with a firewall which constrains the connectivity you may have outgoing from your NAT, but most companies don't have. So as soon as you can establish a TCP connection up to the cloud, you're in business. Because TCP connection, you can have, it's two-way, right? Once it's established, you can communicate in two ways between this. So two TCP connections to the router, and you're in business.
And then, okay, great.
Yes, and so another why Zenoh for ROS developments? Actually, another interesting point is that in Zenoh we try to support a lot of various different protocols. So we support TCP, UDP, QUIC, but also because we designed the protocol in a way that it can work only, for instance, at the data link layer in the ISO reference of networking. It means that we can also implement Zenoh over Bluetooth, over LoRaWAN, over serial ports, serial communication, over Unix socket, over maybe in the future over CAN bus, for instance. So you can really consider to have the same middleware to communicate into various network protocols. So all of a sudden, it will open a lot of use cases when you may have robots communicating with various sensors, either via LoRaWAN, either via OpenThread, or just a CAN bus, for instance, within your robots. And all of this will be accessible through the same API, the Zenoh API.
Okay.
And you can imagine to bridge your ROS2 communication also over those networks if the bandwidth is good enough, right? Okay. And we also provide some integrations with other transport. So we did the bridge for DDS, but in the same way we did a bridge for MQTT, for instance.
So you can connect with IoT devices and integrate it. For example, now I'm very interested on fleet management systems, and then in a fleet management system, you may require also the robots to communicate, for example, with a lift. And this lift has an IoT device that the robot can communicate with it in order to call the lift to come and open the doors for that. So in this case, everything will be integrated, because if we use Zenoh, because it's already able to communicate with the IoT device and with ROS2 internally.
Absolutely, that's the very point. Yes, that's in the same Zenoh system, in the same data plane managed by Zenoh. You can have publication and subscription coming from DDS, bridged via Zenoh, and publication and subscription from MQTT, bridged by the MQTT plugin for Zenoh. You will receive everything in a single Zenoh application or different Zenoh applications that can manage both your robots and your sensors.
Okay.
All what that you need to do, because DDS has its own data format, right, which is CDR encoded. CDR is the encoding for DDS. MQTT, in the MQTT world, usually most of the time is JSON data that are sent, right? So all that you need in your application is to understand CDR data, understand JSON data, perform some data transformation, republish, and you're in business.
Exactly. Yeah. So for the applications to manage the data and the type of messages, that's not a problem. And then the problem is that the messages arrive, right? And they are able to communicate, which is the problem that Zenoh is solving. So how is it pronounced? Is Zenoh?
Zenoh, like Zen.
Okay, like Zen. Okay. Great. And you have mentioned there are several topologies that Zenoh can work, but for me it's not clear. So there are, from your documentation, I found that there are the peer-to-peer, the brokered, and the routed. So can you explain us more about the difference between them?
Okay, so peer-to-peer is really like DDS. So each of your application using Zenoh is considered as a peer and can communicate directly point-to-point with each other peer, which are Zenoh applications. So you have really point-to-point communication between all your Zenoh applications. Okay,
wait. Then that means that each one of them has to have a Zenoh bridge?
No, they just need the Zenoh programming API.
Okay.
So really, we provide API for Zenoh in various languages, so C, C++, Python, Rust, and you just program your application, the logic of your application, using this Zenoh API, which provide very few primitives, mainly put to publish a key with a value, declare subscriber to declare a subscriber, right? Get to perform a request that you will get reply for, and declare queryable, which is actually the server side. So you declare a queryable which will reply to get operation. Okay. That's the 4 basic primitives in Zenoh.
Then my question was wrongly made myself. So it's because I'm moving to the ROS environment. So in this case, we are not talking about anything about ROS.
Yeah, in this case, it's not about ROS, right? It's really a pure Zenoh application.
Exactly.
That can interact with ROS, thanks to the DDS bridge.
Exactly. So we have an element, I don't know, my fridge, that has the Zenoh implement how to those primitives that you mentioned, put, get, and etc. And then this bridge can communicate. The fridge can communicate with my robot, which is a ROS robot, because the ROS robot has inside it the Zenoh bridge.
Yes, Zenoh bridge for DDS.
Okay, and that would be considered a peer-to-peer communication.
So if you can configure your Zenoh bridge to act as a peer, so it can communicate with another peer point-to-point. So with another bridge or with another Zenoh application, for instance, I will directly communicate with it, which can implement directly some logic, not being a ROS application, but directly using the Zenoh API.
Okay, got it.
So, and the Zenoh router. So the Zenoh router is really a routing point. So to which all your Zenoh application and your DDS bridge and your MQTT bridge connect to. And this router will just route all the publication and all the queries, get operation from point to point where they need to go.
Okay. That would be the case. I'm sorry to interrupt you. It's because this subject is a little bit difficult. I know you know a lot about it, but not my case. And also the audience is a difficult subject. So I want to put some like kind of an example in a robot situation so the people can imagine what you are talking. And in this case with the router, what I imagine is I have one robot in one LAN, and then I have another one in another place with another LAN, and each one of them, they have a Zenoh bridge, and then they communicate through the router.
Exactly.
Okay. That would be the router configuration of Zenoh.
Yes. Yes. But if you have one single router, actually, it's similar to MQTT. It's what we name a broker, right? It's a single point that do the mediation between all the clients which are connected with this router. That's what we named a star topology, right? You have one router, a broker in the middle, and all are connected to this broker. That's a possible deployment for the Zenoh router. That's why we say we support broker deployments. But
Okay.
that still with the same piece of software, which is the Zenoh router.
Okay.
But this Zenoh router, in addition, can be deployed in several different places. So, for instance, in your cloud, you may have, if you have, for instance, several VMs in your cloud, maybe in different regions. Right?
Yes, exactly. Different regions.
You may want to have your router deployed in different regions. So you can configure those routers to be interconnected with each other. So establish just a TCP connection with those routers. And then you can have all your robots, so the DDS bridge in your robots, connected to either the router in Europe, either the router in Asia or in America, wherever you want. Still, the communication will occur thanks to the different routers that will route the data from hop to hop up to your second robot, for instance.
Okay. And the same. Then you will consider this also as brokered, the same configuration when you have several routers connected between them. Also, that would be considered a brokered situation.
Yeah, it's similar. It could be considered, if you compare it to MQTT, it will be similar to a federation of brokers. You have several brokers interconnected with each other. The point with Zenoh is that all those routers don't need to be deployed in the same cloud.
Yeah.
You can also have those deployed in various cloud providers. You can even have routers deployed in your edge. So, for instance, in your factory, you can have one router that will route the data between different sublans that you might have in your factory, for instance.
Exactly. So, for example, my computers here in Barcelona, my robot, they can connect to a router which is in Ireland, and then the client which is from Japan, then it connects to a router which is in, I don't know, in Tokyo. But then the router in Tokyo and the router in Ireland, they communicate each other. So then everything is automatically connected, right?
Absolutely.
From Spain to Japan. Okay.
Yes.
Okay, got it. So that is the brokered situation. And then what about the routed situation?
So that's actually the same. So that's really when you have several brokers, we name this router.
Okay.
That's really a routing path. There is a routing path from router to router.
To router. Okay.
To the various clients. Actually, yes, that's maybe we shouldn't. Your point is correct. Maybe we shouldn't spoke about this broker mode because it's. I realize now it might be confusing.
Is it? Yes.
Just to make the comparison with brokered middleware such as MQTT, for instance,
I see.
Which have only one single broker, which is a single router mainly. In Zenoh, we may have several routers, so several brokers that's similar, which are interconnected with each other.
Yes, then I think it's more clear, at least to me, okay, is if we have router and peer-to-peer, and then the brokered is just a special case of the routed one. It's just so then you simplify only two methods and that cover everything, all the possible situations. Yeah,
absolutely. Yeah, that's the point.
Okay, so now I understood this. Very good, very good. And then, okay, so you have answered several about the different questions that I already had here, so I don't think that we need to go into this. And well, one question. This is aside, but one question that I'm pretty sure many people is going to ask, and probably you have heard a lot of times, is, so doesn't the Zenoh Bridge DDS introduce an extra delay in the communications between ROS2 nodes?
So it depends, actually. Within your robot, if you deploy your Zenoh bridge in the robot host and you configure all the ROS to use local host only communication, right? All the communication between your ROS nodes within your robot won't go through Zenoh.
Yeah,
it will communicate peer-to-peer. So no increase of latency here. But as soon as you get out of your robot, right? You will pay a little extra cost because of the Zenoh bridge. But actually, what we measured is that the Zenoh communication increased the latency of just a few microseconds, tenths of microseconds.
Microseconds?
Microseconds, yes.
Wow.
So that's really negligible.
Yes.
Compare this to the latency of your network, which is in tenths of milliseconds or hundreds of milliseconds if you go up to the top.
Yes.
So I would say no.
Okay.
It doesn't really introduce an extra latency.
Okay, great. I want to test this, but very quick. I want to see this. No, that's another. I'm thinking as you are telling me, so I'm getting, I understand now. So I'm thinking about how can I apply this in order to provide a better service to our students. And then one of the points is that when they connect to our real robots, then they can move the robot with a web joystick, and that is on the screen, so they can put the robot on the proper location for their experiments. But then there is a small delay between of a few, let's say 300 milliseconds. Because of all the communication involved in there, and then. Yes, I was thinking about, okay, so having the advantage of ensuring the communication, but adding more milliseconds into this delay because the guys they are far away, so it's those milliseconds, they are understood, they are clear. We cannot do more about that. But if we are going to put even more, that's what I was worried. Then in this case, that is negligible, I think.
Yes, if we added few milliseconds in extra, that will be a problem. Just few microseconds is really negligible.
Yeah. Okay. Great. Then, so you have mentioned a lot of advantages for using Zenoh in our robotics projects. So, can you tell us any disadvantage? So that people can consider, right? Like say, for this project I'm going to, but for this other not because of something.
Mm-hmm. So actually, so far we didn't saw any disadvantage using Zenoh. It brings really a lot of advantages, but if you can find some disadvantages, we'll be eager to know, because we will try to mitigate those disadvantages. So I would say.
Something like, for example, a case in which you would not recommend to use Zenoh.
No, honestly, I can't think, because really, if you need some very specific QSs that DDS provides, but which are not used by default in ROS2 actually.
Mm-hmm.
Zenoh maybe not offer yet those QSs, but with the primitives that we build and with the experience that we have in DDS, we may at some point implement also the similar QS that we have in DDS.
Okay.
So I will say in some very corner cases, Zenoh doesn't yet support some use cases that might be supported by DDS, for instance. But that will be not the majority of ROS2 use cases.
Okay. I see. Then, and also to clarify, you are talking about the DDS, that is the internal layer of, is the communication layer of ROS2. And then, so far, most of people uses fast DDS or Cyclone. Then Zenoh can work with both of them, right?
So yes, Zenoh is supporting the DDS standard. So as soon as the DDS provider, fast DDS, RTI connects,
RTI also,
as soon as they support
right.
the DDS standard communication, Zenoh can work with. Yeah.
Okay.
Because actually, Zenoh, the Zenoh DDS bridge is using Cyclone DDS, and you might know that at the OMG, the standard organization that standardized DDS, they perform some interoperability tests between all the DDS vendors. So they ensure that communication is occurring well between various DDS vendors. Yeah.
Okay. Great to know. Then let me see. About the current state of development. So you have mentioned many situations. So it looks like it's already ready for commercial applications. Is that right?
So actually, yes, there are some companies that started to use Zenoh in commercial applications. For instance, Tractonomy that we work with. Mission Robotics also, which are doing robots for underwater robots. FA Robots, which is a joint venture between Foxconn and AD-Link, which is also using Zenoh. And also in non-robotic use case, for instance, we work with Flex. Flex is a company providing a platform to automatically install and update PLCs, software for PLCs. We are also used by a startup named Everin Fair, which is working as for GPU on demand for machine learning. So they distribute the task for machine learning to various GPUs thanks to Zenoh. Very interesting, by the way, because they made a comparison between gRPC and Zenoh and found that Zenoh performed better than gRPC.
Okay. Awesome. Very good.
We recently, Zenoh is still a young project, right? It has 3 years now. We just stabilized the API in the last version. So in the future version, we will we'll try to make sure that all the API are backward compatible. So you won't have to change all your code to upgrade to a new version of Zenoh. On the protocol side, we still have some changes to do. So I won't say that in the future version, for instance, it will be on the wire compatible with a previous version of Zenoh. But the goal is really to try to stabilize the protocol, to finalize, let's say, the protocol in order to what we want to do in the future, to support the future use case we want to support for the next release.
Okay.
And then we hope that Zenoh will be stable enough. We will just add new features, new transports, new stuff.
Okay, it's awesome. And this project it's open source, right?
Yes, it's open.
And then how do you do business?
So the main part is that we have investors, right? AD-Link is principal investors. We have now a second investors, which is TTTech. TTTech is an Australian company providing certified software for various use cases. And one of the use cases is automotive. So actually, they are very interested in both Cyclone DDS and Zenoh for the automotive use cases. And they will help us also to provide certified version of Cyclone DDS and Zenoh for automotive. So that's the main investors. We may have more investors in the future. Then we also participate to collaborative projects, so European funded collaborative project, research projects. That is a source of income. We will do, of course, support, so paying support for various companies, training for Zenoh use cases. And and that's mainly how we live.
Okay, very good. So I understand. Then, here another of the let's say of the interesting part of the ROSCON, which is Mr. Rust. So I mean the Rust language. That was another one that caused a lot of attention during the ROSCON together with Zenoh. And so you developed, Zenoh is developing Rust language, programming language, right?
Yes, exactly. So the core of Zenoh is developed in Rust. So actually, very interesting because at the very start of Zenoh, we developed it in OCaml. OCaml language.
No idea.
Yes, it's not a very famous language, but it's very interesting because OCaml is used for safety systems because there are a lot of mathematical concepts attached with OCaml, which makes that you can prove your software. So you can make proof of your software with. And that's what we were looking at with OCaml, and that we keep also looking with Rust. It's really the safety of the language. And actually, Rust, I don't know if you know, but recently the NSA, American NSA, provides some recommendation for memory-safe languages. And Rust is one of the memory-safe languages because, let's say, I think the number was something like 70 or 80% of the bug of the critical bugs that exist and that can get used by hackers, right, comes from memory issues, memory management issues, right? And Rust has in its core as the concept of memory safety, so you cannot do weird stuff with the memory of your software. So that was very important for us. And then Rust is really, really efficient. In OCaml, we skipped OCaml because really of the performances. OCaml has a garbage collector inside, and all the language with garbage collector for real-time or close real-time software are not really good because at some point you may have a freeze of your software just for the garbage collector to run and so on. With Rust, there is not this problem. So Rust is almost as efficient as C or C++.
Yes, that's what I heard. And people were very excited at the ROSCON.
Yeah. Yes, and actually, yes, the ecosystem is growing very fast because it brings lots of interest. There are a lot of companies investing in Rust and a lot of open source software, open source libraries also developed in Rust. So we find everything we need for extension of our software. And also it's a very nice language and it's always a pleasure to see that once you manage to compile your software, it's running and it's not crashing.
That's awesome. Yeah, that's awesome. Okay, very good. So expect very soon at the construct a course about ROS with Rust. Then.
Yeah, that will be nice.
Very good. Then, one. So you have API. You mentioned that Zenoh provides APIs to different languages. Which languages are supported?
Yes. So the core is developed in Rust, but with Rust you may have a binding to other languages. So actually we support C. C++ will come very soon. Is currently in development. We support Python. We have also a REST API. And in the future, we'll add more APIs for Java, for Go, for whatever language the user may want, right? But the point is that really at the core, even if you use the C API, for instance, behind it's Rust software. So it's safe.
Okay.
And we also for embedded case, because Rust might be sometimes too heavy. The Zenoh router, for instance, is a few megabytes, so it's not so huge. But still, for embedded platform, it
Maybe
might
it's too
be
much.
too important.
Maybe.
Right? So we provide Zenoh Pico, which is a pure C implementation of Zenoh, and that we will use for on every MCU, for instance. We use it on ESP32.
Okay. So that was my next question. What was Zenoh Pico? Zenoh Pico is are the libraries, the implementation of the Zenoh libraries in C++ for embedded systems?
So in C, not in C++.
In C. In C.
Yeah. So it's targeting embedded system. It supports the core features of Zenoh, maybe not all the features, but let's say the core features of Zenoh. And it also implements various transports. So that's the one we experimented with serial communication, for instance, with Bluetooth, with OpenThread. And still, it's able to connect to a Zenoh router and to communicate with the rest of a Zenoh system, and then to communicate with a Zenoh to DDS bridge, so with your robot.
Okay, great. Then, so how can anybody start testing Zenoh? So it is. You mentioned that it's open source, so I presume it's freely downloadable, and also it's easy to configure in ROS2 and use it.
So so all the code is available on GitHub. You go to the Eclipse-Zenoh project in GitHub, and you'll have all the sources, all the repositories.
I will put a link on the show notes for the audience, so they can find it easily.
And also on Eclipse website, we have a download place where we push all the releases, the binary precompiled version of Zenoh. Mm-hmm. And then for each API, you can get it from your, depending the language, from the management, dependency management. So from PyPy for Python, for instance, from crates.io for Rust, and so on.
Okay.
And for ROS, actually, we made a packaging of the Zenoh DDS bridge as a ROS component. We just need to. The problem is that at this stage, the ROS farm is not supporting the latest version of Rust that we required for Zenoh. So for current version of Zenoh, the buildings is failing on the ROS farm. So it means that you will need to download the ROS package and build it from the ROS package.
Okay, on your own computer.
The Rust environment to build the Zenoh DDS bridge, for instance. And you need some disk space, because Rust for compilation takes a lot of disk space, a few gigabytes.
Okay. Good to know. Okay, but then, so anybody with ROS2 Humble distribution, they can download the packages and compile themselves in their provided that they have this space in the hard disk.
So in the Eclipse download website, we provide either the zip. You just download the zip, you get a binary, you run the binary
directly.
That's good to go. We also provide a Debian repository. So if you configure the apt sources to go to this Debian repository, you just do apt install Zenoh bridge DDS, and you're good to go.
Okay, perfect. And also for today, actually, you have prepared a demo, right? That we can check by creating a project at the construct. So you have created a ROS project, what we call at the construct a ROSject. So in our cloud, there is an area for the students where they can create their own projects. And then you have created one of those projects that we are going to share later on the show notes with a link, so everybody can copy with just clicking on a link, doing like that. Can you share that with us? So how is your...
Absolutely. So let me share my screen. Oh, you need to activate the... I'm not authorized to share my screen.
Okay. Yeah, so that's my fault. Then let me go. This is very easily... multiple participants, done. So now you should be able to share.
Yes. Okay, can you see my screen?
Yes, we can.
Okay, so what I will show you now is this setup. So in here, we have a ROS-ject at the construct, where I will deploy the simulation, the gazebo simulation of TurtleSim, of TurtleBot, TurtleBot 3 burger version.
For ROS2.
Yes, in ROS2 version with using DDS and Cyclone DDS. And I will also deploy and start this Zenoh Bridge DDS that will do the bridging between DDS and Zenoh. And it will be connected to a Zenoh router that I will deploy in my cloud. So in any cloud instance, you can use whatever your cloud you prefer. And this Zenoh router also is started with the REST plugin, so that's the REST API of Zenoh. And from this REST API, you can connect to a web page that will connect to this REST API. And you will see that we will be able to publish and subscribe to ROS. So the publications that I will allow from the Zenoh Bridge DDS are just the laser scan, so the topic scan, which is translated in Zenoh as a CMU RT scan. And for subscription, the CMDVAL to receive the twist messages. And so it will subscribe to CMU RT/CMDVAL.
Okay. And your cloud, so the just a second for the image, this one. Yeah. So for when it says your cloud, this is the Zenoh router that we have been talking before, and then this is already launched in another cloud of yours.
Yes. So at this stage, for today's demonstration, it's deployed in a cloud accessible as demo.zenoh.io.
Okay.
The point is that you can, for your demo, if you want to reproduce this demo, you deploy it wherever you want.
Okay. Yeah. And then
choose your cloud and you deploy it.
Exactly. And then the browser, it's launched in your local computer. And
so yes, the browser will be in my local computer. And it can be in your computer. It can be in whatever
exactly
in the world.
Exactly.
That just need to access to this web page. Then to connect to the cloud here.
Actually, I can, for example, if I wanted, I can also put my browser, point to that address, and then I will get at the same time as you the same information there.
Absolutely.
Yes. It's just to clarify the architecture and how everything connects. Okay, great.
So let's do this. So in here, I have the construct simulation. Here in this shell on my host, I have a remote connection here to the cloud. So here I will just disconnect, and you see I just SSH to my cloud, so demo.zenoh.io.
Where you will launch the router.
Where I will launch the router, exactly. So I'm just going into this directory, so this one, and I'm starting the router.
Zenoh router, okay.
So the name of the router is just a binary named Zenoh D. Zenoh D as Zenoh daemon.
Okay. With some configuration that you have some files for that and so on.
So here, no. Here it's without any configuration. It's just the router without any configuration.
Okay.
For this demo, I don't need to configure anything. It's already opening a TCP port to listen for Zenoh communication. It's already by default loading the REST plugin, and the REST plugin is listening on port number 8000.
But how do you say to the Zenoh daemon that needs to load the REST plugin? If it's a plugin, you should specify somewhere, right?
No, by default, it's this one. The REST plugin is always available by default.
Okay. I understand.
Zenoh router. You can, by configuration, deactivate it to not be started, but we choose by default to be active by default in order to have the REST API always available.
Okay. Makes sense.
So now in here, I will start
inside the ROS-ject.
So this is in ROS-ject.
The ROS-ject.
Actually, yes, I have this shell in the ROS-ject. So in here, I will start the Zenoh Bridge DDS with a configuration file. Actually, so in this configuration file, I will show you after I configure which topic I want to route over Zenoh.
Okay.
And I also instructed here to connect to my Zenoh router on demo.zenoh.io
Okay.
with this port number, which is default port number used by the Zenoh router 7447. So if you want to reproduce this, you just replace this demo.zenoh.io with the IP address of your cloud
Okay.
where you deploy your router. Okay. So it's up and running. It's connected to the cloud.
Okay.
So I have this web page that I can refresh. So this web page, you see, it's this IP address. So here it's served only by Apache web server. So it's just to make available this HTML file.
Okay.
So this page is a single HTML file which embeds some JavaScript for the Zenoh connectivity. So here, it's by default instructing to connect to demo.zenoh.io where my REST API is running. If I use another cloud, I will change here the IP address again.
Okay. But so far we can see nothing on the, we can see just the web interface, the basic interface, but we can see no data from the simulation.
Absolutely, yes, because nothing is started in ROS yet, so nothing is routed by the bridge. So now I will start the simulation. So in this here, you can see already that we are receiving the logs from the robot. So that's the topic ROS out.
On the web page, we are receiving.
Yes.
I'm sorry, I'm describing a little bit for the audience that is listening to the podcast. Yes. So, go ahead.
So here, the web page received already the ROS out logs coming from the robot. Those logs have been published over DDS, received by the Zenoh bridge DDS, routed over Zenoh to the router, and then routed to the REST API and to the web browser here.
Exactly.
Which subscribes to the ROS out topic. And you see also the laser scan image here, which is also subscribed by the web page. So the laser scan published by the robot are received by the bridge, routed to the router, and then routed to the plugin REST plugin API, which publish this to the web page. The web page is receiving laser scan and just plotting the point for the laser scan image.
Yes, that is what the robot is sensing at present.
Yeah, exactly. That's so you see the gazebo here. We get the exact same image from the LiDAR. So all the blue line are the laser points coming from the robot, and they are getting back and computed as a distance for each angle from the robot. And we get here the exact same plotting from the LiDAR. Okay?
Yes.
And now I can also, from this web page, perform some publication of twist messages from the web page to the CMDVAL topic. So just pressing on the key here.
On the arrow to go up.
And we can see the robot which is moving.
Yes. So you're controlling the robot from the web page.
I'm controlling the robot from the web page.
Through the
Zenoh. Up to your simulation in Barcelona.
Exactly. Well, actually, this cloud is in Ireland.
Oh, yeah. You know, but it's working anyway.
Yeah, it doesn't matter. Yeah. So the cloud is in Ireland. Great. Then you are sending the web page is sending the command belt topics. Those are received by the REST API of the router, of the Zenoh router. Then the Zenoh router receives that, and then it redirects back into the Zenoh bridge DDS, which is in the simulation. And then from there goes straight into DDS, into the topic of the simulated robot.
Yes.
Great.
Exactly. Yeah.
Great. Awesome.
So, and now what I can show you in addition is an example of usage with Zenoh Pico. So
okay.
I have this ESP32 right, with a gyroscope sensor, actually. So when I power it on, it's booting. It's automatically connecting to my local Wi-Fi.
Okay.
And Zenoh Pico inside is running, starting up. and automatically connecting to the Zenoh router in the cloud in the same way than the browser is connecting to it. But here it's using Zenoh communication. It's not going through the REST API. It's really going to the Zenoh port 7447 of the Zenoh router for Zenoh communication.
Mm-hmm.
And each time I move this this ESP32, the gyroscope detects it, and the robot is moving. So twists are sent from the ESP32 up to the robot. So here I'm moving the robot forward. Here I'm moving it backward. No.
Okay.
Right.
So this device, it's connected to the router itself also.
Yes.
Using the REST API also.
No, it's not using the REST API. In this case, it's using directly the Zenoh connectivity. So it's using the Zenoh protocol directly on TCP, over TCP, to communicate, to publish twist messages up to the CMD-val topic that will be routed from the router to the bridge and then to DDS.
Okay, great. Can you show a little bit more, because I missed a few seconds of, I'm going to stop so you can talk and you appear showing the on the camera because of the configuration.
Okay, so I'm starting from where I show where I boot the ESP32?
No, it's okay. Everything was clear, but just showing on the camera that you are moving the device. Yeah.
So here, if I twist on the right, the robot is moving on the right, twist on the left, moving on the left, and then I can go forward and go backward.
Awesome. Yes, and we can see here also on the web browser how it is actualizing the lasers as the robot moves. So the full communication in all the sensors is performed at the same time.
Yes, exactly. So here I already demonstrate that in the same data plane, you have connectivity to the cloud, web connectivity thanks to the REST API, but also connectivity with a simple MCU, just a ESP32. And all of this going through the NAT, right? Because I guess in your cloud you also have a NAT behind. So everything is working fine.
Awesome.
And then I have a last demonstration of integration. So I will show the picture for this one. So actually, that's the picture of the demonstration as just show with ESP32 in addition connected to the Zenoh router.
That was the example. This slide that we can see now on the screen is the example of the device controlling by the inclination and using Zenoh Pico on the microcontroller.
Exactly. Yeah. So now another step in the demonstration is integration with IoT. So here I have a Raspberry Pi with a ZigBee key. So that's really this setup, the Raspberry Pi, the ZigBee key, and the software ZigBee to MQTT. And also on this is running the Zenoh bridge to MQTT. Okay. So this bridge is actually routing some publication and subscription from MQTT on those topics. ZigBee to MQTT device button for this button, press button that I have here, and subscribing to ZigBee device bulb set for this bulb, light bulb that I have here, which will change the color depending on some publication I make via Zenoh over Zenoh router going to this bridge to MQTT. Okay. In my local laptop here on my Mac OS environment, I will start just a Python script using Eclipse Zenoh in Python. It will subscribe to the publication from the button, and in reaction of this receiving message from the button, it will publish some twist on CMD-val.
Okay.
So if I push the button, it will move the robot, spin to the right or spin to the left. Okay. At the same time, this same script is also subscribing to the scan topic, so to the laser scan, right? The code will just consider the front angle and will get the minimum distance from the laser in the front side of the robot. And depending the distance with a wall, it will change the color of the light just with a publication over Zenoh to the bulb topic to change the color, and this publication will be routed to the bridge MQTT and then to MQTTs and to change the color of the bulb.
Awesome. Yeah. Wow. That's very interesting to see the whole thing working.
Yes. So here, I'm starting this simple script.
This is your local computer and you are launching...
This is my local computer, yes, exactly. So here I need to turn up to a wall so we can see here the color is already changing.
But how are you turning the robot to a wall?
So here right now I'm in this same script. Actually, I'm also listening to the keyboard.
Okay. So
and then
so the key
on the arrow key.
Okay.
To send some twist to the message. So it's really the simple teleop, same code that ROS2 teleop with the arrow key to drive.
Yes. Okay. No problem.
So here you can see there are some twists which are published. So here it's moving, approaching to the wall, coming to orange, and now it's red.
Yes.
And you can see here also in the log we also subscribe to all the publication over Zenoh to ZBig to MQTT, and we can see all the MQTT command going from the script to the light bubble, but also going to the web page here, because the web page is also subscribing. So we can see exactly what the message are coming from Zenoh to MQTT and so on. So now if I move back the robot, you see there are some publication to change the color of the light, and it's going back to green. In
real time, as the robot moves far away from the wall, so we can see the change in the colors. So it's based on the distance of the robot. This is sent to the router, then sent to your program in your local computer, and then your local computer decides which one color to set the bulb. And then this is sent again to the router and then back into the MQTT device that you have in the lamp, and then changes the color.
Absolutely, yeah. And
awesome.
Actually, I made the deployment this way, but you can do the deployment in another way. The point is that this Python script that is subscribing to both ROS2 and MQTT via Zenoh can be deployed anywhere. It can be also deployed in the Raspberry Pi with MQTT, and not necessarily connecting to the router, but also connecting directly to the MQTT broker that will route up to the router. Or it can be deployed in the ROSject, so in the construct sim, and it will run the same.
Okay, awesome.
In the other way, so we have also this button, right? So if I push the button, you will see here the script here is receiving the push command for the button, and it's sending a twist to the robot to spin in a way. So we can see here also the reception of the button, the press button here, which is this payload in JSON, which is a single click. If I do a double click, here we receive a double click, and the robot is spinning in the other way.
Okay, that would be an example of not only receiving commands to an IoT device, but also sending commands.
Absolutely, yeah. So we have two-way communication from
exactly.
ROS2 to MQTT and ZigBee, thanks to Zenoh.
Awesome. Impressive demo. Let me tell to the audience that we are going to share this project also in the links of the show notes, so you can implement by yourself, test by yourself. And it contains also some instructions about how to launch everything and get it on business. Okay. Great. Awesome demonstration, Julien.
Thank you.
Awesome. Then we have to be finishing here, so I have still a few questions more. The first one, but I think that you already answered, is about the name of Zenoh. Where does it comes from? You mentioned about Zen. What?
So yeah, no, it doesn't come from Zen actually.
Okay.
Actually, it's come from Zenoh, the Greek philosopher. Zenoh.
Yes, I know this one. Oh,
Because,
yes.
yes, Angelo Corsaro is a huge fan of Zenoh, a Greek philosopher, because of this paradox of small infinity
Yes.
that he made a very long time ago. And actually, that fits well with what we're trying to achieve with Zenoh, because we, at the very core of Zenoh, is really the protocol for which we try to be as sparse as possible in terms of overhead of the payload. So we design the protocol in a way that in some cases, in most of the cases, you can go up to only 5 bytes of overhead with regard to your data for each messages. And that allows us to go over very constrained networks such as Bluetooth, for instance, for which you have only 20 bytes of payload. So Zenoh is also a play of word with zero network overhead. Zero network overhead, which what we try to turn to approach is really to have the smallest overhead possible for the protocol in order to save bandwidth, save energy, and just be more efficient.
Okay, awesome, very good. I like the both senses of the word, of the name, of the protocol, and that's a framework, right? If I say properly, it's a framework rather than a protocol.
It's both, actually. We implement the protocol, so there is a protocol implementation that we for the time being, it's internally specified, but we hope in the future maybe to open the specification of the protocol. So that's the Zenoh protocol, but there is also the Zenoh framework, all the software stack that is built on top of this protocol.
Okay. Makes sense. Okay, and so tell me, what are the secret plans of the future of Zeta Scale? Something interesting.
So future is really to keep focus on extending the scope of Zenoh use cases. We want to add more transport, right? So for instance, we have the basic as TCP, UDP, QUIC, WebSocket also. We have WebSocket, but soon we'll work on LoRaWAN. Maybe in the future CAN bus or any other transport that might be useful for robotics, but also for IoT, IIoT, or any communication that need to do. Also to add more APIs, so Java API, Go, maybe some, JavaScript is an important one that we would like to support very soon. More integration, so we already have MQTT, DDS. We also have, by the way, we didn't spoke about the storages, but for storages technology, we support InfluxDB, ROXDB, just a file system. So we want to add more databases support in the future, and also integration with other protocols. So we might consider, for instance, to interoperate with Kafka, with OPC UA at some point. There's a lot of different protocols in order really to ease the integration between various systems in various topologies and connectivities.
Yes, exactly. So we can communicate between one and the other in a transparent way.
Yes, exactly. Yes. Awesome. And you can integrate legacy systems that you may have that are using MQTT, DDS, MQP, or whatever, with other legacy system and with new system based on Zenoh.
Okay.
And then another part, very important part, is that we are working on certification of first Cyclone DDS, which is in progress, and also Zenoh Pico, so certified version of the software for critical use cases such as automotive, transportation mainly. Okay, awesome. Now a lot of people know your secret plans. So thank you very much for sharing to let us know. Welcome. My pleasure.
Okay, let me ask you a final question. So we are still listening about the changes that happen at the end of 2022, where Open Source Robotics Corporation was acquired by Intrinsic. And then I would like to know your opinion about this. So is that good for the ROS community? What is your opinion?
So, as you may know, actually, Angelo Corsaro, our CTO, is a member of the ROS TSC, right? Mm-hmm. So he had the chance to be on the TSC a few months ago, where Intrinsic was here to answer questions to all the open source robotic community, right? And actually, what he heard was quite reassuring. So Intrinsic seems to really want to support all the ROS ecosystem in open source. And I think, in my point of view, that's also good that at least Open Robotics gets some financial support to support this ecosystem, which is increasing a lot, right? We all know that open source software is very nice, but has a cost, right? In terms of developer, you need to pay the developers for it. And sponsorship is one option, but also, having big companies or small companies with some capacities to support those open source software is really, really important. It's the same for us, right? We are not just benevolent developers, right? We are paid by Zeta Scale, which is sponsored by investors such as AD-Link, Entity Tech. And it's nice that Open Robotics gets the same source of finance, because it will help them to increase the ecosystem, to increase the support. And we just hope that Intrinsic will keep the open source way, and still have this very great community of developers around. Okay, very good. So thank you very much for sharing your thoughts about this situation. And that's all for this interview. Thank you very much, Julien, for coming here and having this clear, I would say, quite introductory, in-depth introduction to what it is and what can we expect as ROS developers on this. So thank you. Thank you very much, Ricardo. Thank you to allow me to present Zenoh, and we hope to talk to you soon about the future evolution we may have in the future for Zenoh and robotics. Okay, the mics are here for you, so whenever you need. Thank you. Thank you. Thank you very much. Thank you. Goodbye. And for all of you there, that's all for today, okay? So we got here almost 1 hour and a half here, so it's okay for today. So what else can I tell you? So send me feedback. What do you think about those episodes? What you would like to be featured? And problems that you can see, I don't know. So the sound, the questions are silly, whatever. Tell me so we can improve. And that's all for today. See you next week with a new lesson from the experts. And until then, keep pushing your ROS learning.